In this video, we're going to talk about 7.1 in our book, Integral as Net Change. So let's consider particle motion where the derivative of position, that's the ds dt, is also known as the velocity, and that's equal to t squared minus 8 over t plus 1 squared. So we're going to be interested in where t is between 0 and 5, and we're going to graph this. So a good window for us, we can do it with our x and y. So our t is going to be the x, and our y is going to be the velocity. So you can choose your x min and x max to be 0 and 5, and your y min and y max to be negative 10 and 25. So if we graph that, it's going to look something like, I believe it's going to come and look something like that. Now, we're asked to describe the motion of this. So using our calculator, let's go trace. So if you hit the trace button, and then after you've hit trace, you just hit 0, then you should see that our velocity at time 0 is negative 8. So we can say then that our particle is moving at 8, and we were told this is centimeters per second, so it was moving left at 8 centimeters per second at time 0. And then if you hit trace and then you put in the 5, so I'm saying x, but it's the same thing as t equal to 5, then I believe you're going to get something like 24.8, so 24.8 centimeters per second. So at the end of that 5 seconds, our particle is now moving 25.8 centimeters per second to the right. And I didn't draw this real great. If you hit the trace button and you move it and try to get close to where this velocity is going to be 0, then I think you will find that it's not exactly, but it's about 1.25 seconds that our velocity will be equal to 0. So we would say then that one way to describe that motion is, the particle is moving 8 centimeters per second to the left at time 0, and then gradually it came to a rest and at about 1.25 seconds, then changed direction and went to the right, increasing in velocity until at the end of that 5 seconds, it was moving about 24.8 centimeters per second. Okay, so that's a description of the motion. So I'm going to slide this up a little bit, see if we can find the position from the displacement. So if we are told that the initial position was at 9, so our particle is starting at a position 9, and since that's positive, that's going to be 9 centimeters to the right of whatever 0 is. And we want to first know where is that position at time 1. So what we want is to have our position at time 0 and then plus our delta S, our change in position. And that's our net change in position, which is also known as displacement. So in that case, what we want is to, now normally we know that distance is equal to rate times time. That's when the rate is constant, and our rate is our velocity. But our velocity is variable because, as we saw, it is changing with time, and it's going from negative and then over to positive eventually. And so what we want then is our displacement, our delta S, that change in position, we're going to have to kind of imagine that we're summing that up. So if we were thinking in terms of kind of the microscopic level, we would take the velocity at some time period and then multiply that velocity times a very small delta t to get the displacement over that little time interval. And then we could increment that a little bit and then get the velocity at a little bit bigger time and multiply it times a little delta t, and that would give us maybe our next little change in position. So it's this idea of thinking about what's happening kind of on that micro level, where we can describe what's happening on that level. And then if we imagine that we sum all of those up, and that would then, taking those velocity at small time increments, times a little bit of delta t. So we're adding up those delta s's, and to get an approximation to that change in position, that displacement. Then as that limit of the delta t's goes to 0, then this leads to an integral. And so what we want is that integral from 0 to 1 of v of t dt is going to be that change in position. So what we want for the position at time 1 is going to be our starting position, that's the s of 0, plus that displacement, that net change in position that we're going to get by integrating that velocity from time 0 to time 1. And since we were told that s of 0 is 9, we'll get 9 plus, and we could do this one by hand, but just in the interest of expediency here, we can go ahead and throw that on your calculator. And I believe because our velocity was negative over that interval, you're going to get 9, and then that'll be minus 11 thirds. And so we're going to get that's going to be 16 thirds or 5 1/3. So our position from time 0, where we were 9 to the right, we have moved back left towards wherever the origin is, and our position then at time 1 is going to be at 5 1/3 or at 16 thirds. So now let's talk about where our position is at time 5. So at time 5, it's that same idea. We're going to take our position at time 0 that we know, and then we're going to get our displacement or net change in position from time 0 to time 5, and that we can do again on our calculator. So we will get 9 plus, and that turns out to come out even to be 35, and so that means we are going to be positioned 44 centimeters, and since that's positive, that means to the right of the origin, or 0. So again, this 35 is representing a net change. We saw, I'm going to go back here, we saw that our velocity was negative over part of that interval and positive over the rest of it. And so for a while, our particle was moving to the left, and then it paused for a moment, and then it turned and went to the right. So we have different results when we're talking about displacement, which is what this 35 represents. That's our displacement over those 5 seconds. Our position has to account for where did we start, because our displacement is going to be from whatever our beginning position was, and that's going to affect what our ending position was. Now, it's a different question also when we want to know the distance traveled. So here, we don't want the fact that we were moving to the left for part of this time interval and then moving to the right. So those are going to kind of cancel each other out. So at some point, we're going to be back to where we started. We want to count like the actual steps we're taking. So that distance traveled then is going to be that delta distance is going to be the absolute value of that velocity at some point there, and then times a little delta t. So that will give us that little bit of distance we traveled, and again we'll sum that up. So our distance traveled is going to become an integral. It's going to be that integral from 0 to 5. So now starting position doesn't really matter, and it'll be the absolute value of v of t dt. And if you do that on your calculator, you'll get, I believe, 42.587. So that's going to be centimeters that we actually traveled, kind of like counting your steps. So what we're trying to get here, we're just beginning our discussion of this, although we have done some of this already before in our experience from our AB days, is that we want to, in the case of modeling, where we're trying to solve a problem that's coming from a real life situation, is that we want to describe that situation on a differential level. What's happening in that very small increment of delta x or delta t. And that might be in the case we talked about here, where it's a distance that we're traveling, but there's many other applications this can be used with as well. Then we want to proceed in describing the situation as if we were going to approximate our result using a Riemann sum. So if we can describe what's going to happen in that approximation stage, then it's a small step to go to the integral to actually describe what's really going to happen there with more precision. And then once we can get that, this is the hard part, is getting, well, first I think the description part, coming up with this part is the hardest. And then moving to the integral. Once we get to the integral, then it usually becomes pretty routine. Either it's something we can do pencil and paper fairly simply, or if not, we're going to be able to use our calculator to do that. So here is an example. The car is moving with an initial velocity of 5 miles per hour. So our velocity at time 0 is 5. And we are accelerating at a rate, and this is now our acceleration, is going to be 2.4 miles per hour per second. So that's kind of a strange unit there for 8 seconds. And we want to know then how fast is the car moving after those 8 seconds. So what we're trying to do here now, in maybe an unfamiliar situation where we're talking about velocity and acceleration, is that our velocity as it increases, so our velocity at some particular time is going to be what it was to start with, and then plus that change in velocity, which is going to be our acceleration at some value then times delta t. And so this is going to represent how much then our velocity is going to increase over that small increment of time. And then we're going to sum that up, and as the delta t goes to 0, we're going to get that our velocity after 8 seconds is going to be our velocity to start with, that velocity at time 0, and that's going to become an integral from 0 to 5 of our acceleration. And oops, I want to make that a plus, not an equals. And so that's going to be then, since our velocity at time 0 was 5, then we're going to add that to the integral from 0 to 5, and our acceleration was 2.4 dt. And we can do that pretty simply, pencil and paper or using your calculator. That's not really the issue, and that should be then an 81.8, and that's going to be in miles per hour for our answer. So our velocity or speed, since it's positive, after 5 seconds is going to be 81.5 miles per hour. So let's move up in a different, so other than a particle motion kind of problem here, we can say that in this example, from 1970 to 1980, the rate of potato consumption in a country was C of T, C for consumption, is 2.2 plus 1.1 raised to the T, and that's measured in, our consumption is measured in millions of bushels, and this rate is millions of bushels per year with time 0 in 1970, and we want to know how many bushels of potatoes were consumed from the beginning of 1972 to the end of 1973. So we're going to get the potatoes consumed are going to be, this is a rate right here because that's in millions of bushels per year. So we're going to take the consumption at some moment in time, and then times a little delta t so that when we multiply that little bit of years times the bushels per year, we're going to get the bushels of potatoes consumed over that small increment in time. That will lead us to summing those up, that C of T sub K times our delta T, and then that, of course, as delta T goes to 0, is going to become an integral. So we're going to get an integral of that consumption, and our delta T becomes a dt. So again, that's, if you look at the units, that's in millions of bushels per year times time, the number of years, is going to give us bushels, millions of bushels consumed. Now to think of our limits here, if we're going from the beginning of 1972 to the end of 1973, so if we think of, and time 0 is in 1970, then the beginning of 1972 is going to be 2, and the end of 1973 is actually going to be 4. And so we want to do our integral from 2 to 4 of C of t dt, where the C of t is given by that. That's, I think, probably best done with our calculator. And if you do that, I believe you're going to get 7.066. And our units there is going to be millions of bushels of potatoes consumed over that 2-year period. Okay, we'll slide up a little bit here. So work is equal to force times distance. This is our constant force formula. So assuming here that the force is going to be constant, and force you can think of a lot of times as being like weight. So pounds is going to be a unit of force, and in metrics, we will see that force is measured in newtons. So that's what this is representing here. So if we're an English measure, we get this weird thing like force in pounds times distance, a lot of times measured in feet. So your work might be something like foot-pounds, which seems strange unless you have done a lot of physics. In metrics, the force is measured in newtons, and from what I have found, 1 newton is the force that's needed to lift a typical apple, and then the distance is going to be in meters. And so when you get a newton meter, a newton times meters, that's known as a joule. And so a joule is the work done in lifting an apple 1 meter. Kind of crazy. So Hooke's law for springs. So we're thinking now springs, so these might be something like they can go anything from like a really tiny spring you might see in a watch to those really big thick ones you might see in the suspension of a car. But Hooke's law for springs says that the force needed to stretch or compress a spring x units from its natural length is a constant times x. So that is, the force needed is a constant times x, where K is going to be our force units per unit length. And that's a characteristic of the spring. Is it a really thin spring like a watch spring, or is it a really thick, stiff spring like something in a car? And that's called the force constant. And then the x then is going to be our distance. So here's an example of that. So it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done stretching the spring 4 meters beyond its natural length? So first, what we need to do is use Hooke's law here, and we know that the force is going to be 10 meters with a distance of 2 meters. So that's going to allow us to solve for that force constant K. So 10 is going to be equal to K times 2. So that means our force constant in this case is 5. So that makes our force equation now look like F equals 5x. So again, this is now a variable force. So the idea is when you have the spring, as you start to stretch it, initially when you're just moving it a little bit, it's not going to take a whole lot of force. But the more you stretch it, the more force it's going to take, the more resistance you get from that force. So it's a variable force situation that we're talking here. And now we want to know what is the work done. So we want to think of in the microscopic level, the differential level, the work that's going to be done in moving this a little bit of a distance is going to be that force, which is going to be our 5x, times the distance, which we're going to move it a little delta x. So we'll figure out what the force is based on how much the spring has been moved or stretched so far. And then times a little distance will be a little bit of work. Then, because the spring is stretched, we'll have to recalibrate what the force is for the next delta x. And so you're going to imagine that you're adding up these delta works. This is our Riemann sum idea. And then as the delta x goes to 0, the summation is going to become an integral. And so the work done is going to be that integral of our force function, and that delta x is going to become a dx, and we're summing that from 0 to 4 meters beyond the natural length of that spring. And so we can do that. That's going to be 5/2 x squared going from 0 to 4. When we plug in that 4, we'll get 16. So that's going to be 5/2 times 16 minus 5/2 times 0. So we can cancel the 2 with the 16, and we'll end up with 40. And since our measurements were in newtons and meters, a newton meter is going to be what we have called a joule, and that's a unit of work. All right, very good.